Hi again. Do you remember on the first day of class, the very first day of class, and then again in the last in-person class we did before the spring break that shall never be spoken of, I showed this video of a protein folding spontaneously. It starts out all elongated in a string, and then it wiggles and jiggles into some final configuration. And over on the right, there's a graph of some quantity, and what we see is that this protein folds and wiggles and jiggles until it finds this minimum in whatever this quantity that is being plotted. So it turns out that the quantity being represented here is called the Gibbs free energy, calling it G. And there is this equation that I've said is what we're shooting for in this class because turns out to be incredibly predictive and useful. It governs processes in molecular biology, chemistry, the environment, climate, astrophysics, basically any process that is happening in an open container. The expanse of beautiful things that this equation can describe is so bewitching to me that I'm trying to figure out how to incorporate it into my next tattoo. Anyhow, so that's what this video is about. It's about arriving at and understanding the predictive value of this equation right here. The process that we're going to use is we are going to start by introducing something called the Clausius inequality. We're going to show that the Clausius inequality is in compliance with the second law. And then from the Clausius inequality, we're going to derive an expression that connects the Gibbs free energy to the second law, and that is this expression here. We're going to talk about why this was a useful thing to do and return to that protein folding picture. So to introduce the Clausius inequality, that's the first step. What we're going to do is start by this idea that we had at the very beginning of class, that the work done by a reversible process is the maximum amount of work we can do. It is greater than the amount of work we can extract from any other process we can think of, or basically all other irreversible processes. For the whole of this video, I'm going to have a greater than, less than, and equal sign. And I want you to know that the equality part pertains to when the generic process that we're referring to is reversible, and the inequality part refers to when it's irreversible. Okay. So thinking about the amount of energy that leaves the system when we're doing this work, the energy leaving the system in the form of work, its energy is leaving the system, so it's usually negative. So because of that, because it's negative, I can rewrite this equation this way. And then I can rearrange this equation to get this inequality. For now, we're just going to hold on to that. Now, let's picture this. Let's picture I've got two processes, and these processes go between the same initial and final state. One of the processes is reversible, and one of the processes is irreversible. You can picture this as being a pressure-volume diagram, but really it can be any two state variables. But we're just going from some initial state to some final state. For each of these processes, I can write down the first law. I can say that the change in internal energy from state 1 and 2, or for state 1 to 2, is going to equal the amount of heat transferred in and out of the amount of energy transferred in and out of the system in the form of heat and work. And this is true for the irreversible process, but it's also true for the reversible process. And because I'm going between the same initial and final state, then actually these two parts of the equation are equal to each other because the change in internal energy will be equal to each other. So from this, I can write whoops, that's a W. I can write that equality. And you can rearrange this equation to arrive at dq reversible minus delta q, delta w minus delta w reversible. All right, this here is why we did this little mini derivation. So I can see that this side of the equation is equal to greater than or equal to 0. So what we have is delta Q reversible minus delta Q for any process is greater than or equal to 0. Arbitrarily now, I'm going to decide to divide by t. I'm going to divide everything across by t. And what we can notice is that this quantity here is our thermodynamic definition of entropy. So I'm going to rewrite this in terms of entropy, bring this to the other side of the equation, and arrive at ds is greater than or equal to the heat transfer divided by temperature. This is the Clausius inequality. And I want to point out that what we used to arrive at the Clausius inequality was we used the first law. We used the thermodynamic definition of entropy, and we used the idea that reversible work is the maximum amount of work we can get out of a system. So these three ideas led to this Clausius inequality. I'll point out for the last time in this video, I think, that the equals part of this inequality refers to when it's a reversible process, and the inequality part refers to when it's an irreversible process. Okay, so now we've introduced the Clausius inequality. Our next step is to show that the Clausius inequality is in compliance with the second law. So to do that, let's consider an isolated system. And an isolated system, recall, is one where no matter and no energy can come in or out of the system. In this case, by definition, the heat transfer is 0. So we have that ds must be greater than or equal to 0. Okay, well, an example of an isolated system is the universe. So consider the universe. So we're talking about the change in entropy of the universe, and recall that we've divided the universe up into two sections. We've divided it up into a system and a surroundings. And we get that the entropy of this isolated system must be greater than or equal to 0. And what we've essentially rewritten here is our definition of the second law. So two things to point out, that the second law, the rest of our definition of the second law says that this is for a spontaneous process. Well, from the perspective of the universe, if you go out that far, everything that's happening is a spontaneous process, or at best, a reversible equilibrium process. Because recall, the equal part is for reversible and the unequal part is for irreversible. But then also, what we get is we've now conflated the terms spontaneous and irreversible. So because this inequality refers to irreversible process, what I hope you're coming to is that spontaneous processes are irreversible. What you just heard was my dog barging in on us. Okay, so what we did along this path was we did show that this Clausius inequality is in compliance with the second law. There was another thing that happened, which was because we used our thermodynamic definition of entropy to arrive at this equation, this also serves as a validation of that definition. in a way, we showed that this definition is also in compliance with the second law. Okay. Our last step then is to, now that we believe this Clausius inequality is something useful and predictive because we've connected it with the second law, we're going to go from this inequality to our expression for the Gibbs energy. Okay. So the first thing I'm going to do is I'm going to move this term to the other side of the equation. And I'm going to multiply through by t. So far I've assumed nothing, just done some math. And the last step, though, I am going to assume a constant pressure system. Recall for a constant pressure system that the heat transfer is equal to the change in this state quantity called enthalpy. Now, this constant pressure assumption is going to confine the usefulness of our Gibbs energy equation to systems that exist at constant pressure. That is a limit of our model. But I'll also say that constant pressure, and most processes that are happening in an open container are reasonable approximations of constant pressure systems. So there are many processes you can model in molecular biology, chemistry, climate, and astrophysics that obey this modeling limit. All right, so making this substitution then, I arrive at TdS minus, oops, it's partials now, minus dH must be greater than or equal to 0 according to the second law. Okay, something magical happened here. What happened was we had a path function here that depended on the type of process that we were using, and it also pertained to heat transfer from the surroundings. What I have here now is a version of the second law that is written in terms of entirely state and system state variables. Similar to when we derived enthalpy and when we first introduced entropy, it's going to turn out that this grouping of state variables arrives so often that we decided to give it, humans decided to give it its own quantity, its own state quantity. So Josiah Willard Gibbs was the person that stumbled across this one, and he defined the Gibbs energy to be enthalpy minus T times entropy. So then if I use this definition of the Gibbs energy, I can write dG is less than or equal to 0. Notice that there was a multiplication by -1 that got from this equation to this equation and reverse the inequality to be so that it's in the direction we're more used to seeing. And this was what we sought to derive. So recall that we've actually been looking for this equation all along. Remember the bouncing ball example? All along we've known an equation like this should exist. So in the bouncing ball example, we start out with mechanical energy in the system in the form of potential energy due to gravity, and then we end up with a form of energy that is distributed in the form of heat in the table, say. And energy is conserved through this process, but what we never see is a ball that's sitting on a table spontaneously start bouncing. And even though there is no violation on the conservation of energy in that picture. So we decided there was a story that we developed where we began to think about how, well, there's types of energy in a system that are more useful than other types. And so maybe the energy that we can use as work is equal to the mechanical energy in a system, less the amount of energy that is stored in a kind of randomized fashion. So conceptually, we knew something like this, some idea like this should exist, and now this concept you can see is exactly mapped onto this equation, where the Gibbs energy represents the amount of useful energy in a system, and it's related to the mechanical energy now represented in enthalpy and this type of randomized energy. Okay. The last thing is to say why this was useful. Well, actually, I've said it all along, which is that so many systems obey a constant pressure modeling constraint that this equation is widely useful, and its value is that it's now all in terms of state system variables. But let's return to the protein folding just to bring it back full circle. So what's happening? Recall the level Lennard-Jones potential? As the protein folds and jiggles and atoms begin to get closer to each other, they're beginning to find their low energy point on this Lennard-Jones potential. And this represents the enthalpy of the system. As atoms get closer and closer, the mechanical energy from the Coulombic interaction is finding its minimum. So we are decreasing the amount of enthalpy, which is in a spontaneous direction. But this protein is now being confined in space because these atoms have to be close to together. Entropy would rather that it gets to be expanded and exploring all over the space. So what you're seeing in this protein folding built video is a balance between the mechanical forces that are trying to drive the protein to clump and the randomization forces that are trying to let this protein stay expanded. And nature here is finding a balance in the middle.